Welcome to the rigid body equations of motion. Today we are going to discuss various simple problems in rigid body dynamics. And we will begin with the following example. We are to consider a rod of negligible weight and length L having mass points of equal masses m attached at its ends. The bar rotates uniformly about an axis passing through the center of the bar and making an angle theta with the bar. And what we are interested in this particular case is to calculate the torque acting on the bar, both in the intrinsic frame and in the laboratory frame. Now the diagonal form of the inertia tensor is very straightforward to find. It should be the one given here, and the components of the angular velocity written in the body frame should be the ones listed here. So then it's simply a matter of putting everything into the Euler equations, and we should obtain that the torque, as seen in the body frame, has the expression here. So in terms of the coordinate system attached to the body, but then we can convert this through the transformation that we used many times before. We can convert this to an expression in the laboratory coordinates, which is the one given here. And we can try to do this calculation in the laboratory frame from the very beginning. So what happens in the lab frame is that we choose it in such a way such that the angular velocity of the rod is parallel with the vertical. So then the rod is oriented along the k prime axis. So this is just the figure axis of the rod, and then we can, again, using the inverse transformation, we can write this in terms of the laboratory versors. In doing that, if we focus for, let's say, we just need to look at one of the mass points, as the other one will have mirrored coordinates with respect to it. So for, let's say, the first mass point, the position vector should be the one here, given the orientation of the rod. And then if we just take its time derivative, we can find its velocity, and knowing this, we can calculate the angular momentum. So the total angular momentum, taking into account both particles at the ends of the rod, should be this one, hopefully. And if we just apply Newton's second law and take its time derivative in the laboratory frame, this has to be equal with the applied external torque, and the result is the one here. And this should coincide exactly with the one obtained above, so hopefully the derivation is correct. Now we are to consider a right circular cone of height h, half angle alpha, and uniform density, rolling on its side without slipping on a horizontal plane, the motion having the period tau. What we want to do this time is to find expressions for the angular momentum and kinetic energy of the cone. So first of all, we would want to calculate the volume of the cone, and we can do this by assuming that let's say the cone is just resting on its vertex, on its tip, and then in cylindrical coordinates, it's very simple to calculate the volume. It follows from this triple integral, and it should be given by the value here in terms of the constant a, defined as you see here in terms of the height of the cone and the half angle. Then it is also a very straightforward matter to calculate the position of the center of mass of the cone relative to its vertex. So I'm assuming right now that the geometric configuration is that the cone is resting on its tip with the essentially its base is normal to the vertical. So then the center of mass will be about it will be exactly three quarters up the height of the cone when measured in these coordinates. And then, so relative to the vertex of the cone, it's very easy to calculate the principal inertia tensor. But the expression I've written here is not written with respect to the with the point on the vertex. So but with respect to the center of mass. So it's simply a case of calculating it at the vertex and then using the parallel axis theorem to find the corresponding value of the moments at the center of mass. And knowing this and going further, the Euler angles are given as follows. So we can calculate phi straight away, since we know the period of for the motion of the cone in the laboratory frame. So it's given by this. Theta should be a constant angle, which is once again determined by knowing the half angle of the cone. And psi follows from knowing that the rolling is done without slipping, and it should have this value. So then the angular momentum separates into the motion of the center of mass and that of the mass distribution of the cone above the center of mass. The calculations are straightforward, but you need to be very careful not to make mistakes when doing all the involved transformations and so forth. Hopefully I've managed to write them correctly, so they should have the expressions here, where of course you can, if you really want to write everything explicitly, we know this time derivative, the value of this angle, and the moments of inertia are calculated from the elements of the diagonal tensor right away. So hopefully these are the expressions in the laboratory coordinates, and then for the kinetic energy, the same separation in center of mass and rotational motion about it holds, and the expressions should be the ones here. Now we are going to look at a different kind of problem, namely, we assume that an automobile starts from rest with one of its doors open at a right angle, and the door's hinge is facing forward. So it's a slightly artificial problem, as the car doors aren't really designed to work this way anymore due to security reasons. So you can still find them on vintage carriage models and such. But it's still an interesting problem just to go through in order to understand the concepts of rigid body motion. So we have this kind of car, and it starts to move with an acceleration f that is constant, and we are interested in this particular geometrical configuration. We would like to be able to calculate the time in which the door closes. It is assumed that the door's radius of gyration is about the axis of rotation is given by the value here, and we also know that the center of mass is at a given distance from the hinge. And once we find an expression for the time, we are to evaluate it for a specific value of the acceleration and for a door shaped as a uniform rectangle having this width. So we're assuming that the car is moving in the x direction in the laboratory frame. So the door is initially in the yz plane, and then the angular momentum acting on the door is so the angular momentum of the door is then simply the vector here, and if we take its time derivative, in the laboratory frame we obtain immediately this expression. So this has to be equal with the applied torque just by virtue of Newton's second law, and the torque itself is going to be the cross product between the radius vector of the center of mass and the applied force. And again, I'm assuming, when writing this explicitly, I'm assuming that the coordinate system is shifted in such a way such that the center of mass lies in the xy plane. So with that assumption, the cross product is given by the expression here. This is the center of mass vector, and then the applied force, again just by Newton's second law, is the mass of the door times its acceleration. So putting these two together, we obtain an equation of motion that is really just a pendulum equation, and knowing that we can write the moment of inertia in terms of the radius of gyration, we can recast things in the form here. So we've worked with such equations before. We know how to integrate them. The integration follows through these very simple steps. And what is important to note is when we reach the end of the derivation here and we take the square root, we need to choose the negative root for the time derivative of phi, because we need to keep in mind that the angle is actually closing as time advances, so we need a negative value of the angular velocity. Right, so obtaining this expression, we just integrate it for time, and if we want to end up with the time it takes for the door to close, then the value tau here is going to be given by this constant multiplying this integral, which is taken from the what we assume to be the initial value of the angle all the way to pi over 2. And to calculate this, we just make the change of variables here, and we should end up with this expression, where this integral can be very easily evaluated with the Gauss-Chebyshev method that we used before, and the numerical value is the one here. Now, in order to evaluate this further, we need to calculate the moment of inertia explicitly. So we can calculate the moment of inertia for this particular geometry of the door initially about the center of mass. So assuming we are rotating about a vertical axis going through the center of mass, and the result is the one here. And then we can calculate through the parallel axis theorem, we can find the moment of inertia which corresponds to the rotation about the hinge, and so the value is simply this one. And then using the definition of the radius of gyration, we can find the value of the radius in terms of the distance from the hinge to the center of mass. And then using this in the expression that we found above, we can finally find this form of the time. And if we just put in the numbers for the distance and the acceleration, the numbers which were specified previously, it follows that the door would close in a little bit over 3 seconds. And we can think of a similar problem that involves a uniform gravitational field. Namely, we are to consider a door made from a thin, homogeneous material having a given width W. Initially, the door is considered to be opened by 90 degrees, and then it is released, and it is observed to close in 3 seconds. Assuming frictionless motion, we would like to find the angle between the hinges of the door and the vertical. So we begin by calculating the moment of inertia of the door for an axis of rotation that is passing through the center of mass and is parallel with the height of the door. So we need to perform the integrals here. We are assuming that in the intrinsic frame, or in the body frame, the door is distributed in the xz plane. So there is a vanishing mass distribution in the y direction, and then the result is the one here, and we can use the parallel axis theorem to immediately find the moment of inertia for the rotation about an axis passing through the hinges of the door. Then the gravitational potential energy at the center of mass is simply given by the product between the total mass of the door, the gravitational acceleration, and the height of the center of mass, and we can immediately write the z coordinate by using the inverse transformation contained in the Euler matrix, in the rotation matrix given in terms of the Euler angles, and keeping in mind that there is no mass distribution in the y direction in the body frame, we just end up with the x and z components from the body frame multiplying the associated Euler angles. So this is the general expression of the potential energy, and then the total energy which is conserved is just going to be given by the rotational kinetic energy of the door plus the potential energy. And since it is conserved, it has to be equal with the value of the potential energy when the door is closed and at rest. And then we essentially what we have here is a differential equation for the angle psi, which we can integrate immediately for time in order to find the expression here. And we can manipulate this further through this change of variables, and we get that the total time in which the door closes is given by this square root multiplying the integral here, which should be exactly the one that we stumbled over in the previous problem, so we can evaluate this in the same way. And knowing the time taken for the door to close, we can then just solve the equation for the angle, and we should find that it has a very small value, which is of approximately 1 degree and 20 arc minutes. And still considering the motion under uniform gravitational field, we can now look at the problem of a homogeneous cube of sides L, which is initially at rest in unstable equilibrium in such a way that one edge is in contact with a horizontal plane. The cube is given a small angular displacement and is then allowed to fall. And we are to find the angular velocity when one face contacts the plane if the edge in contact cannot slide, and in a second case, if the plane is considered frictionless and the edge can slide. So looking at the first situation, what we want to do to begin with is to calculate the moment of inertia for a rotation axis that passes through the center of mass and is normal to the face of the cube. So we need to perform the triple integral here, which is very simple and should lead to this result. And then we can use the parallel axis theorem to find the corresponding moment of inertia for rotation about an axis going through one of the edges of the cube. So for the case of a fixed edge, this will be the moment of inertia of interest. And to calculate the gravitational potential energy for the center of mass, we just need to evaluate the z coordinate of the center of mass, and the value is the one given here. In this case, we are assuming that the angle theta is measured from the horizontal surface to the diagonal passing through diagonal line passing through the center of mass. And then we just once again use the conservation of energy. So the total energy at any given point in the motion is going to be given by the rotational kinetic energy plus the potential energy, and this has to be, so the value at the end of the motion when one face is going to be in contact with the surface has to be equal with the initial value when the cube was at rest in unstable equilibrium. And we can solve this straight away for the value of the terminal angular velocity, and we find the expression here. Now in the second case, what happens is that the cube no longer rotates about the edge that is in contact with the surface, Rather, it rotates about the center of mass, while the center of mass itself is falling under gravity as the edge slides on the surface. So the total energy will include the kinetic energy of the center of mass, and this can be immediately calculated, since we can find its velocity just by taking the time derivative of the z coordinate. And then once again, using conservation of energy, we should find the value here. So it's slightly faster in the second case as opposed to the first situation. A similar situation follows in the case of having two thin rods of equal masses m and lengths l, which are connected to an ideal hinge and locked at an angle of pi/6 with a smooth horizontal surface. We are assuming that the initial moment the hinge is unlocked, and we would like to find the speed with which the hinge hits the floor, and we would also like to know the time it spends falling. So now each of the rod will, as they slide on the floor, they rotate about their as the rods slide on the floor, they rotate about their centers of mass. So what we want to do is to calculate the moment of inertia for rotation about an axis passing through the center of mass and being perpendicular to the rod. And the result should be this one. And if we are assuming that the entire system is in the YZ plane, we can easily write the Z and Y coordinates for each center of mass in terms of the angle between the origin of the coordinate system, which is assumed to be at the middle beneath the hinge, and the center of mass. So knowing these coordinates, we can calculate the corresponding components of the velocity, and we can calculate the squared velocity for each rod, for the center of mass of each rod. And then the total energy will just involve a factor of 2 over a sum of the kinetic energy of the center of mass plus the rotation about the center of mass and the potential energy of the center of mass. And the result is the one here, which has to be equal with the initial potential energy of the system. So we can solve this straight away for the moment in time when the hinge has hit the floor, and the angular velocity follows immediately as having the value here. So the total speed of the hinge is given by this value. And if we go back to the general result and integrate it for time, for the total time of fall of the hinge, we immediately end up with this result. So it's this constant multiplying an elliptic integral, which can once again be evaluated through the Gauss-Chebyshev method to result in the value here. Now we will look at a uniform rod in a slightly different arrangement. Namely, we will consider that the rod slides with its ends inside a small vertical circle of radius rho, and we know that the rod subtends an angle of 120 degrees at the center of the circle. We would like to find, for the dynamics of the system, the length of an equivalent simple pendulum which mimics its motion. So the first observation is that half of the length of the rod is given by the value here, so it's just the radius of the circle and the times the cosine of a 30-degree angle, which follows just from the basic geometry of this configuration. And this allows us to immediately calculate the total length of the rod in terms of the radius of the circle and the distance from the center of the circle to the center of mass of the rod, which is rho over 2. And now the dynamics is as follows. The rod rotates about its center of mass, about an axis going through the center of mass, and which is perpendicular to the rod and to the circle. So the corresponding moment of inertia is immediately calculated has to have the value here. And now we need to consider that the total energy involves the kinetic energy of the center of mass itself as it moves inside the circle. Then there's the rotational kinetic energy of the rod about the center of mass and the potential of energy of the center of mass in a uniform gravitational field. And we need to put all of these things together with the fact that energy is conserved, which leads to a very basic pendulum equation, which shows that the length of the equivalent simple pendulum is simply the radius of the circle. We are now going to look into the problem of a compound pendulum, which is assumed to be placed in a uniform gravitational field, and it consists of a thin rigid body suspended by a point different from the center of mass. So it's oscillating about the point of suspension. We are to find the period of small oscillations in terms of the radius of gyration above the center of mass and the separation from the point of suspension to the center of mass. Furthermore, if the periods for 2 points of suspension at different separations to the center of mass are the same, the question is, how are these separations related to the length of the equivalent simple pendulum? To answer this, we look first at the moment of inertia for rotation about an axis perpendicular to the pendulum and going through the center of mass. And we write this in terms of the radius of gyration of the compound pendulum. And then by the parallel axis theorem, we can write the corresponding moment of inertia about an axis parallel to this one, but being separated from it by a distance r in some direction along the pendulum. So this would be the moment of inertia of interest in case of rotation about an arbitrary suspension point, and then the kinetic rotation energy the kinetic rotation energy should be given by the formula here. The potential energy is likewise of a simple expression, and once again the energy in the system is conserved. So putting all of these together, we obtain immediately the equation of a simple harmonic motion for oscillations having a low amplitude, and the squared frequency of oscillation is just going to be have the value here given in terms of the radius of gyration of the compound pendulum and the separation distance from the center of mass to the point of suspension. So then we have three identities that we need to keep into consideration. So we are assuming first of all that for two different points of suspension that are located at different separation distances from the center of mass, the periods would be the same. So they would be given by these formulae. And at the same time, we would like to have the period of the same period written in terms of the unknown length of a simple pendulum. So right now it's the unknown value L. So from the equality of the first two relations, we obtain the formula here. So from the equality of the third relation with either of these two, we will obtain the first formula here. You just use them together and add them up to obtain this result, and by putting the first two together, you obtain the second result. And then it follows immediately that in these circumstances, the length of the equivalent simple pendulum is just the sum of the separation distances of the 2 points of suspension to the center of mass. After discussing these simple examples, we are now going to focus on the way of setting up equations of motion explicitly in the Lagrangian formulation. And the first such problem concerns a uniform bar of mass capital M and length 2L, which is suspended from one end by a spring of force constant K. and the bar is constrained to swing freely only in one vertical plane, while the spring itself can move only in the vertical direction. So the two generalized coordinates that are of interest here are the elongation of the spring x and theta, which is the angular deviation of the bar from the vertical. And then we have first of all the problem of the motion of the point of attachment of the bar, which consists in the kinetic energy of this motion plus the potential energy of the spring, which is elastic in nature. And then there's the problem of the bar swinging about the point of attachment. So there's the rotational energy of the bar together with the gravitational potential energy of its center of mass. And then it's very simple to just write a Lagrangian from these four terms and derive immediately the equations of motion to find the equations of a simple harmonic oscillator for the spring and a pendulum equation for the bar swinging about the vertical direction. A more complicated example will involve a double pendulum made out of rigid bodies having a finite extension. Namely, the first one is a plane pendulum consisting of a uniform rod of length L and negligible thickness, having a total mass m, which is suspended by one end in the vertical plane, and the other part of the double pendulum is a uniform disk of radius a, having mass capital M, that can rotate freely in the vertical plane about its attachment point. So we want to find the Lagrangian equations of motion for the system. Involving the rotational component of the motion, we need to consider the two moments of inertia of these two systems. So the I1 corresponds to the swinging of the rod about its attachment point, and then I2 is just the swinging of the disk about its own attachment point at the other end of the bar. So then the rotational kinetic energy will be given by their sum. The total potential energy of the system is gravitational in nature and involves first of all the displacement of the center of mass of the rod and the displacement of the center of mass of the disk. And then we also need to keep into account that the center of mass of the disk itself swings along with the rod, so we need to calculate its kinetic energy as well for this problem. And its Cartesian coordinates will be given by the expressions here, so it's straightforward to calculate the square of its velocity. So then, putting all of these things together, the Lagrangian will be given by the kinetic energy of the center of mass of the disk, the total rotational kinetic energy of the system, and the gravitational potential energy. And then upon deriving the equations of motion, we should obtain these two results. And in order to check if they are correct or not, you can compare them with the equations of motion for the simple double pendulum that we have derived all the way back in the first chapter, and you should see that they have an analogous structure. For an example regarding how to properly solve the equations of motion, we can look at the case of a homogeneous disk of radius a, which is set to roll without slipping down a flat inclined surface, making the angle alpha with the horizontal. The disk's plane is always normal to the inclined surface, but the disk may rotate about the normal. So we are to find the motion using the method of Lagrange's undetermined multipliers. We begin from the constraint of rolling without slipping, which implies that the velocity of the center of mass must be perpendicular to the angular velocity of the disk, so the constraint is of this form. And then if we write it out explicitly in Cartesian coordinates attached to the inclined plane, so the two components of this relation would look as follows, where the um, the angular velocity has been written in its components in the laboratory frame. And so these are coordinates attached to the inclined surface, and accordingly the potential energy of the center of mass of the disk has this expression. And so the Lagrangian itself is given by the kinetic energy of the center of mass of the disk, the rotational kinetic energy for the two rotational degrees of freedom. So phi is just the angle, the angle for a rotation about the local vertical, while theta is just the rotation of the disk about its symmetry axis, and of course this is the potential energy. In order to include the constraints, we construct the additional Lagrangian L prime, which consists of the previous function, to which we attach the two constraints via two undetermined multipliers. And now we've recalled that we've had a detailed discussion about this point in chapter 2. I will not repeat it here, but I will only state that the correct equations of motion for such constraint problems were deduced to be of the form 227, and their list follows accordingly. So we have these first three equations, which are a bit more complicated, and the fourth one has a simple solution and allows us to find the angle phi as a function of time immediately. Then for theta, what we do is that we insert the previous two equations of motion in this expression, and then we make use of the constraint equations as well, and that ultimately leads to the equality here. And by also taking into account the value of I, so this is the moment of inertia for rotation about the disk's symmetry axis, we can then integrate this straight away, and the result should be something like this. And knowing this function, then we can once again go back to the equations of constraint, and we can find x and y. So the calculations are very simple but quite lengthy and a bit tedious, so hopefully I haven't done any mistakes either in the calculation itself or when typing these down. But the one check that we can make to see if this makes sense or not is to see what happens when alpha goes to 0. So these two terms then vanish, and you are left with the disk going around in a circle, which looks plausible enough. And finally, as an interesting discussion, we can look at a slightly more complex problem, which is that of a uniform sphere of radius a, which would roll without slipping on a horizontal plane. What we want now is just to find the Lagrange equations of motion using undetermined multipliers, and to also look at possible conserved quantities. Once again, the constraint on the velocity is of this form, and it translates into the two Cartesian components of the velocity being related to the components of the angular velocity in the laboratory frame. And the complete Lagrangian has a fairly simple form, just the kinetic energy of the center of mass and the rotational kinetic energy of the sphere. And given the sphere's symmetry, this is quite simple in terms of a common moment of inertia, which you can calculate straight away to have this value. So to this Lagrangian we append the two equations of constraint via undetermined multipliers, and once again by application of equations 227 we can derive the list of equations of motion. And what we see from the third one straight away is that the z component of the angular velocity is conserved. And now what's important to note is that the total energy, which is just the sum of the translational and rotational kinetic energies, can in fact be written due to these constraints can be written entirely in terms of the components of the angular velocity. So really the energy separates in a translational term of this form, together with a rotational term which involves only omega z. But as we have seen, this quantity is conserved and the total energy itself is conserved. So what follows immediately is that the two components conserve separately. So the rotational kinetic energy is conserved and the translational kinetic energy is also separately conserved. But in summary, I have discussed various simple problems in rigid body dynamics. The topics that were addressed have included the application of torques and motion constrained by fixed surfaces. We have discussed rotations about the center of mass or fixed axis, motion in a uniform gravitational field, and the equivalent motion of a simple pendulum with respect to a more complicated system. And in the following, we will discuss the more advanced problem of the heavy symmetrical top having a fixed point. So with all that being said, I want to thank you all very much for watching. I hope you found these discussions worth your time, and I will catch you later. Goodbye.